Welcome to the Expo presentation for Team 29, tasked with designing a telemedicine robot. Our advisor is Curtis Wang, and the team members consist of myself, Andres Saavedra, Christian Velez, Erick Alvarez, Henry To, Jose Martinez, Manuel Ibarra, Mario Martinez Cisneros, Miguel Cano, Reynaldo Aguirre, Stephen Vu, and Yi Ni Aung. The agenda for our presentation will be split into various sections where I'll provide a bit of background on the topic of telemedicine and the scope of our project. Then each sub-team will discuss the technical progress for their portion of the project. And finally, Yi will provide a summary and share our future plans. So to start, I have to clarify, what is telemedicine? Telemedicine is the practice of remotely providing healthcare to patients. This requires no physical contact between the physician and the patient. And why is it necessary? There have been recent increases in telemedicine as our reliance on technology increases and social distancing has become a normal practice. We can also eliminate the need for unnecessary doctor's visits and reduce the risk of infectious disease from spreading within hospitals. The current state of telemedicine robots has proven its place within the medical field, with robots already being used in hospitals and more complex robots in development. With the current pandemic, telemedicine robots are more widely available than ever before, with costs typically starting at $4,000. At these prices, a demand for a low-cost telemedicine robot is present. The scope of the project includes the design and development of a low-cost telemedicine robot with the following capabilities. It will have driving capabilities for safely maneuvering through patients' homes. It will have an extendable torso, wireless networking capabilities including transmitting audio and video in real time, as well as the ability to manipulate a gripper and measure body temperature. This Gantt chart highlights the schedule for the entire duration of the project. Phase 1 consisted of conducting research for components and material selections, system architecture design, and requirements for the robot's capabilities. Phase 2 consisted of producing more detailed CAD and schematic designs, as well as coding and implementation plans. Phase 3 is the current phase, which is supposed to consist of fabrication, assembly, and simulation. But due to the restraints of the pandemic, shipping delays and the lack of in-person meetings have affected our progress. These are the functional requirements for the robot that will be fully explored by each sub-team in the technical progress sections. On this slide, we have a breakdown of the sub-teams for the project. The robot body consists of two teams, the base platform and central chassis team. The base platform team is made up of Miguel Cano and Erick Alvarez, and the central chassis team is made up of Christian Velez and Reynaldo Aguirre. The central controller and camera team consists of Stephen Vu and Mario Cisneros. The robotic arm was also split between electrical and mechanical sub-teams, with the electrical team consisting of Aung, Andres Saavedra, and Jose Martinez, and the mechanical team consisting of Manuel Ibarra and Henry To.
My name is Miguel, and my team member is Erick, and we will be presenting the base platform. Here we compare the current design with the old design. The old design's total weight was about 33 pounds, with the total cost being about $204. The new design is 16.2 pounds and costs $34.42. Comparing the old with the new design weighs 16.3 pounds less and costs $169 cheaper. Here we have the base platform design concept. The design features a mount for the telescopic torso subsystem, a housing for batteries and other components, a motor gearbox mount, and a free joint on the front legs that allows rotation for step climbing capability. The design is powered by 6 DC motors, and on the right we have a zoomed-in view of the gearbox and DC motor mount. One of our subsystems requirement was to be able to support the total weight of the robot of 60 pounds. To test the strength of the 7075 aluminum design, an FEA simulation was performed. The design was fixed about the wheel mounts, pin and bolt connectors were added, gravity was applied to simulate the weight of the frame, and the 80-pound force was applied to the base. The stress plot generated is shown on the right. The maximum stress experienced by the frame was 99.6 megapascals, which was below the yield point of 505 megapascals. A motion analysis was performed to test the step climbing capability of our design. Gravity was turned on and a 60-pound force was applied to the top of the base. The design was only able to climb the steps when all 6 motors were used. The minimum kinetic friction coefficient required to climb the steps was 0.75 and 0.76 for static friction. 12-inch wheels were also required to climb the average step size of 6 inches. Here we have the motor torque required on each wheel to climb steps. The maximum torque required from our motors was about 2,000 Newton meters.
Hi, my name is Erick Alvarez. I'll be talking about the DC motor control and the batteries for the robot. We will be using the BeagleBone Blue in order to control the DC motor. It is Wi-Fi and Bluetooth compatible, which will allow the doctor or nurse to have control of the robot from a distance. The BeagleBone Blue will allow us to create a kill switch so that the robot avoids running into obstacles. The motor comes with a built-in optical encoder, which can help us, which can help the robot detect its surroundings. It also allows for 103 Newton meters of torque, which is fairly high for a DC motor. Next slide, please. So this is the code that was made for the motions of the DC motors. On the right side, you can see that the motors are now initialized and all the motors are on and the base stays idle. And then it decides to move in reverse to the right. In this picture, we can see the motors are moving forward, which motors are moving forward or in reverse, and then the user lets go of the controls. This is our power consumption data table. This is worst case analysis, as in all the components are using maximum power at the same time. In order for the microcontrollers to last 40 minutes, they need 7,600 milliamp hours. And in order for the motors to last 25 minutes, we need 20,000 milliamp hours. Because there are so many components, we thought it'd be best to have 2 separate batteries. This is the one for the vehicle-based platform. It's easy to integrate with DC motors, and it's designed for multi-motor use, which we'll need for our 6 motors. This battery will be used for the rest of the robot. It is a rechargeable, high-capacity lithium-ion battery, and it can last up to 2.5 hours. Lessons learned. Originally, we had a weaker motor, so we had to find a stronger motor with a higher torque. And then we had to use a lighter aluminum oil to shave off some of the weight off the platform. And also, to move up the steps, we need to create a gearbox for the rear wheels to create a higher torque and a more affordable DC motors. And we also learned that the wheel size and type are important for step climbing.
Hi, my name is Christian Velez, and I work with Reynaldo in the central chassis team. A scissor lift design was chosen for the chassis of the robot, and here is a slide displaying the current design next to the previous design, which is at the bottom left. Overall, the specs remain the same, but the whole design was changed to accommodate more space for other subteam components, like the base of the lift, as you can see here. Rods were also applied for added support. And going into the current design, the scissor lift is able to support the experienced load, the effective load of 40 pounds, 30 from added components, and 10 from the scissor lift components itself. The force required to raise a load of 40 pounds is 110 pounds. So the actuator design that was chosen was a power screw driven by motor to provide a mechanical advantage to the design. In order to determine motor size and screw design, the drive torque was determined to be 10 pound-inch to lift the load. This current ball screw design is able to provide a lift the robot in a total of 9 seconds at 75 RPMs. And in the next slide, the chosen motor will be discussed.
So to accommodate the new central chassis design, we have now decided to use a bipolar stepper motor. And this stepper motor will have a holding torque of about 10 pounds per inch and will cost about $18. Due to the lack of physical hardware for the central chassis, we opted to create a text-based code simulation. Here we can observe an actual code that could flow in an actual simulation. For this slide in particular, the motor is initiated and the central chassis is currently collapsed fully down. The user will lower the chassis but be stopped by the lower limit switch protecting the scissor lift. And in the second demo here, the user now wishes to higher the central chassis fully, extending it up. And like before, the upper limit switch will activate to stop the stepper motor from rotating further. Some things learned during the project was that we should use a different microcontroller, as the BeagleBone Blue wasn't compatible with later components we wish to use on the central chassis. And regarding sterilization, we hope any future teams can test and prove which methods are effective due to the restrictions preventing any testing for now.
Hello, I am Steven, and this is my partner Mario, and we are in charge of the central controller. So this is the original design of our central controller and its networking. It's showing how everything is connected from the user towards the server, and from the server towards the central controller.
Object detection was successful using precompiled models along with the Google Coral and the Google Camera. Image classification inferencing was successful using pre-trained models, Google Coral, PyCoral Git directory, along with the Google Coral and its Edge TPU. Object detection was achieved by using precompiled models and a pre-built demo application called Edge TPU Server, which points to the precompiled models. We can see a live view using the Coral camera running through the Edge TPU and the model. We can see the live object detection inferencing on the screen. Next slide. This is a flowchart of how I achieved how I retrained the image classification model using option A, which goes from Python machine learning application to PyCoral API to the Edge TPU runtime, then to TensorFlow Lite. Weight imprinting was used to retrain an image classification model. The demo on the Coral page trains the model to recognize 10 classes. I then added 7 classes, so in total we now have 17 classes. We can always retrain this model to recognize a new class.
So this is the overall flowchart of my implementations of WebRTC. So the host launches the server on a cloud service provided by Heroku. Once the server is initiated, the user establishes a media connection on the handler, which tells the server that the media was obtained. Next, the user sends this info to the server and sends a URL to the patient. And once the server establishes the media connection, once the connection from peer-to-peer is confirmed, they are able to talk to each other via audio and video. Next slide. So in my demo, I am deploying a cloud-based service, Heroku. The terminal auto launches our server with a unique ID, which I will be highlighting at a specific part of my URL. Now I am deploying another link to show that these two rooms have different URLs to provide that these two rooms are unique. Now I send the first link to another computer and it is entered as shown. In the other tab, we will see that the other computer did not join, which is a good thing because we only want the first link that we use to initialize to have the new computer or peer-to-peer connection to show. So at this moment, I am testing if this message is being sent from the second link to the first link, which is not something we do not want, which is shown on the right. So now I am typing from the main computer to my laptop, which is hosting the server. And we can see that hello was shown on the main server. And this is the end of my demo. On the next slide, this is an image of me and myself with my partner Yi in the middle, showing that multiple users can join the server. So the lesson learned at the central controller is that the server is coded to where both the patient and the user must have a camera with a hardware ID to join the server. Otherwise, they cannot join the server. Fixing this issue would require a server to be entirely recoded. Although the server had been self-certified, there were some issues that were apparent as the peers were still not connecting correctly, until I attempted to host the server onto a cloud-based server when trying to test the server through the network.
I had trouble using the MDT to communicate with the Coral board, but was able to use the tool with help from our advisor and was able to learn and use this tool. I also had trouble using PyCoral's APIs in the Coral board, but kept trying to implement these functions by reading more about them on the Coral page until I was successful.
And my name is Aung, and I'm part of the robotic arm electrical team, along with my partners, Saavedra and Jose Martinez. So this block diagram shows how all the electronic systems will be integrated together with the BeagleBone Blue. However, we were not able to implement this system due to the COVID-19 restrictions. So we developed each sensor system as well as the motor system independently and created test benches for each subsystem. These were the finite state machines we developed in the beginning of the year to help us as a guide in implementing our code, as well as these are the finite state machines for implementing the code for distance sensors as well as the deadman switch algorithm. So this is a flowchart for our servo motor test code. And as you can see in the flowchart, a command terminal is used to send the movement command to the BeagleBone Blue, which then uses the robot control library API to run the movement commands on the servo motor. The voltage at the feedback pin of the servo motor is measured using the ADC pin and translated to actual code data using the robot control library API for ADC. And then the position feedback is sent back to the user via the command terminal to relay about the position data and confirm if the movement command was executed correctly or not. And here you can see how we map the ADC voltage to the motor position. A equation was generated on Excel using the trendline functions and graphing through position and voltage data points. With the current setup and mapping yields ADC resolution about 0.04 degree per ADC step as so far.
Hello, my name is Jose, and I'll go in depth with the servo motor. Here you can see the test bench for the servo motor and the schematic of the setup. The BeagleBone Blue is connected to the servo motor signal pin where it will receive the movement commands. The servo motor is also powered by an external 5-volt power source. We updated the circuit to include the ADC port from the BeagleBone Blue and added a voltage divider circuit. The ADC pin is utilized to read the position feedback of the servo motor. The feedback pin is connected to a voltage divider with two 10K resistors to scale the voltage level. The original plan was to incorporate 4 motors, but due to COVID restrictions and limited time, we were only able to test out 1 servo motor. In this slide, we have a servo motor demonstration that shows how the user will control the servo. The user will input a desired position between 1.5 to negative 1.5 inside the command terminal, which in this case is Cloud9. The command will then be sent to the BeagleBone Blue, which will then signal the servo to move to the desired position. The servo motor has a feedback that will let us know if the servo reached the desired position or not. If the servo motor does reach the user's desired position, the terminal will indicate it, and if it doesn't, the terminal will also indicate it.
Hello, this is Andres, and I was responsible for the arm's obstacle avoidance and body temperature measurement functions of the robot. Here we have an electrical schematic that consists of time of flight distance sensors and a contactless thermometer connected to an Arduino Uno instead of the BeagleBone Blue due to reliability issues with the hardware. A total of 5 distance sensors were required for the robotic arm to ensure that the arm is capable of detecting obstacles in every direction, along with the contactless thermometer for measuring a patient's body temperature. These components all utilize I2C serial communication protocol. To use I2C, the sensors were connected to the serial data line and serial clock line of the Arduino Uno. An 8-to-1 multiplexer is also required to connect the X-shut pins of the distance sensors to the GPIO pins, allowing the sensors to be activated and deactivated for taking distance measurements. Unfortunately, the contactless thermometer would not work and was not detectable on the I2C bus, indicating the possibility of faulty hardware. The physical test bench consisted of the Arduino Uno microcontroller with the time of flight sensors connected to an 8-to-1 mux and a temperature sensor on 2 breadboards. The code flowchart for the time of flight sensor demonstrates the functionality of the code. This mostly consists of setting up the GPIO pins, initializing the I2C bus with the sensor API, and running the functions that determine the currently active sensor determined by arm or base movement. If the arm or base are not moving, all the sensors are deactivated. This truth table demonstrates the logic for how an individual time of flight sensor can be activated with the 8-to-1 mux. The select pins determine which X-shut pin from the time of flight sensor stays high, activating the required sensor while the rest remain powered off. The enable pin is normally active low to allow a sensor to be activated. When the robot arm or base is not in motion, the enable pin will be set high, shutting off all the sensors. Here's a quick demo of the time of flight sensor. On the top is the Arduino IDE and serial monitor, and the bottom is my test bench. The Arduino displays an out of range message when nothing is detected, and a value in millimeters when an object is detected. When the object is too close to the sensor, it will display the object detected within range message. When fully implemented with ROS, this would deactivate the arm and base motors and default to a safe state. With all of our research and troubleshooting, the electronics ARM team learned some valuable lessons. We found the BeagleBone Blue microcontroller to be unreliable and overcomplicated for sensor data acquisition. The Arduino, with its vast libraries, would provide a smoother integration of our systems. Another lesson is to avoid purchasing low-quality components. The MLX90614 contactless thermometer was not detectable on the I2C bus, most likely due to faulty hardware or inadequate soldering onto the breakout board.
Hi, my name is Henry, and I was assigned to design the mechanical arm with the help of my partner, Manuel. These are an overview of the robotic arm. On the image on the left is the robotic arm itself, and the image on the right is the end effectors. Here is a tray table of the different materials we thought of using for the mechanical arm. We chosen 6061 aluminum because of FEA purposes, high mechanical properties, and its low cost. This is a tech drawing of the mechanical arm. Its reach is roughly around 2 feet, which is close to one of our requirements for the robot. Also, its overall weight was around 6 pounds per arm. This is an image of the servos being set up inside for the shoulder. This is how the servos would be set up for the elbow. Each servo would have a 2-to-1 gear ratio set up to increase that torque output. Here's a stress analysis with a 20 Newton force applied at the end. Next slide. Oh, oops. This is a displacement of the arm where most of the deformation. Oh shoot. Here's the stress analysis of the arm. I mean displacement of the arm where most of the deformation happened at the end of the link. Next, here are some plots and motion studies on analyzing the torques of the stress of the servo at each joints. The maximum output torque that is needed to move the entire arm with a 10 Newton force at the end is around 2.7 Newton, which is within range of the servo torque output at the shoulder. At the elbow, the maximum torque output was 0.85 Newton meters, which was also in range of the servo at the elbow.
This is Manuel Ibarra, and I'll be talking about the end effectors and camera arm. This is a trade study of some of the considerations we had when finalizing our selection of an end effector. We ultimately went with a 4-bar linkage end effector, mainly for superior power and stability. This is a drawing of the latest end effector we came up with. It is a change from the originally proposed end effector that only used one servo. This gripper design will use dual servos with a stall torque of 15.5 kilograms per centimeter, and when complete, will weigh a little over 1 pound. Some of the gripper features: the gripper will be made out of 6061 aluminum. It will open up to a max width of 5 inches, as shown in the middle image. On the rightmost image, we can see the self-lubricating oil light sleeve bearings. They will be placed at each joint and give the end effector a good balance between strength, wear resistance, and durability. So I chose a rubber gripper because with the use of 3D printing and rubber casting, we can create a custom grippers that fulfill specific needs that may arise. This gripper design in particular has holes perforating the midsection of it, so that when the end effector is grabbing an object, the rubber gripper will conform to fit it and provide a sturdier grip. On the rightmost figures, we can see the FEA analysis on the rubber gripper where a 6-pound load is applied. As predicted, the gripper has more deformation towards the center as it complies to the shape of the object it is coming in contact with. A new addition to the robot is a camera arm. As our previous design was going to have a camera mounted on the end effectors, whereas the camera arm will reside atop the robot and be able to bring itself closer to better assess the patient. The maximum reach is a little over 22 inches. It will be made out of PLA and will have a weight of about 1.17 pounds. The camera arm will use 4 FT117M servos. A coral camera placed at its end will have an 87.6 degree field of view. As seen on the middle figure, it will be able to rotate about its base axis. And on the rightmost figures, we can see there will be a servo at the very end of the arm, allowing the coral camera to also rotate independently.
So this about wraps up our technical progress part of the presentation. Now I will present about our future plans as well as the summary of the project. As for the near future plans for the mechanical team, we would like to perform the SolidWorks simulations using PLA materials instead of the aluminums for certain components, as well as perform the robot assembly simulation for the entire robots with all the components assembled. We'll also like to decrease the overall weight of the robot, as well as increase the amount of degrees of freedom and assign new gearboxes to improve performance in certain areas. For the electrical team, we would like to develop test bench and test scripts for the FSR and IMU, which were delayed due to the defective BeagleBone Blue units, as well as implement MUX integration with multiple sensors. So switching on and off of multiple sensors can be achieved, especially with distance sensors. We'll also like to implement ROS between the primary and secondary microcontroller communications in order to send commands to retrieve data from secondary microcontrollers. We'll also like to work on retaining object detection model using Docker. And finally, we'll like to complete documentation on our test scripts and codes for easier knowledge transfer to the next team. In terms of recommending the future development plans for the next year's team, we'll like to recommend integrating rods to sensors and motors to send movement commands as well as receive sensor data. We'll also like to recommend to migrate distance and temperature sensor data acquisition units to Arduino instead of BeagleBone Blue due to easier integration with raw serial and the reliability issues on the BeagleBone Blue. We'll also like to integrate different electronic subsystems on the via the sensor hub PCB that can be custom made, and as well as achieve the physical assembly of the robot, as well as decrease the overall weight of the robot. So in summary, the mechanical teams was able to complete the CAD design and CAD design of the mechanical parts and perform analysis on those components, which included FEA analysis and motion study. The electrical teams was able to test electrical components individually in test bench environments. However, all those different components and subsystems were not able to be integrated together due to the COVID restrictions. So that about wraps up our presentation, and we'll be hosting a Q&A session during our live presentation on May 6th. Thank you for your time.